But anyway, so there's some basic information right there. Not too much explanation is required, just that, just to kind of, now that we have this new operation we've added to our repertoire. Okay? So any questions on any of these notations or anything like that? Okay. So we're going to be using this one primarily in our class, okay, for right now, because it's just pre-calculus. But you will see all of these if you do decide to take calculus. You'll see all of these used. Okay? Actually, we might see this one show up here later today. We'll see. Anyway, question. This right here? It's an apostrophe. It's supposed to be actually an apostrophe. So it's just like y prime. So y prime is how you read that, like prime. Mm-hmm. Okay, so let's now get into trying to figure out some of these shortcuts. Rather than, if we're taking the derivative, rather than always having to go through this limit process here that we use, let's see if we can come up with some shortcuts. Okay? So, if f of x is equal to 7, find f prime of x. Okay? In other words, find the derivative of this function. Okay? Now, remember, back conceptually, right, the way we learned what the derivative means, it is the slope of the function, or the slope of a line tangent to the function, but those are interchangeable, right? Or the rate of change of this function, the instantaneous rate of change of this function. Okay? Now, the graph of 7, right, what will that look like?
Line.
F of x equals 7, yes. What kind of line? Horizontal line, right? Okay. What is the rate of change of a horizontal line? 0. So what's the derivative of this function going to be? 0. Yeah. Okay. Okay. So mentally, right, mental math, you do it like that. If you want to, let's also go ahead and I'll go ahead and show you the limit definition as well. So again, we'll take the limit as I'm going to use h here instead of delta x again, just because it's a little bit easier to write, in my opinion. Okay. So we'll set up with our basic limit definition here of the derivative, or limit definition for the tangent slope, Okay. Now, in this particular case, if I try to evaluate f of x plus h, what will the result be? If I plug x plus h here into my function, what am I going to get? 7, right? It's 7. Regardless of what I put in here, my answer is always going to be 7. So I'm just going to have 7 minus, and then what's f of x? 7, right? So minus 7 all over h. Okay, it is kind of a face, isn't it? A not very happy face. What is 7 minus 7? 0. So I end up with the limit as h approaches 0 of 0 divided by h. And of course, what's 0 divided by h? It's just 0. And what's the limit as h approaches 0 of 0? Well, there's no h to plug the 0 into, right? So what's this going to equal? Yeah, just equal to 0. So we can do it the really long way with the limits, or you can also just, understand our concepts there and do it real quick. Okay. Questions on that? Yes.
So why did we do? Oh, never mind, because it's just going to be 0. Okay, never mind.
Yep. Okay. So.
Why is f of x plus h become 7 again?
Because what we normally do here is we take that x plus h, right, and we replace it here. We substitute it in, and then anywhere else we have an x, we also have to substitute in an x plus h. Since, there's no x's over here to sub in that x plus h, f of x plus h is just going to be 7. Unchanging. Regardless of what I plug in here, I'm always going to get an answer of 7. Correct. There's no x's. It doesn't change. It's constantly 7. Always 7. Okay. So what can we maybe deduce from here, right? So the derivative of a constant function seems seems to always be, what should it be? If you're always taking the derivative of a constant function, which is going to be a horizontal line, right? What's the slope of a horizontal line? 0. Yeah, 0. Okay? And so in other words, the derivative with respect to x of c equals 0. Okay? So there's one of our first rules, right? Really basic, but now we no longer need to use the limit definition of the derivative every time when we see a constant. When we take the derivative of a constant, we know the answer is going to be 0. Okay? It's got to be 0. Okay? So what's the derivative of 100? 0, right? What's the derivative of e? 0. E is a constant, right? E is something like 2.67, 2.76, I don't know, something like that, okay? Derivative of e, 0, okay? Derivative of the natural log of 2, 0. Natural log of 2 is a constant, right? Doesn't change. It's always just natural log of 2. Derivative of natural log of 2, 0. The derivative of sine of pi over 3, 0. Sine of pi over 3 is a constant. Take the derivative of that, 0, okay? Derivative of sine of x, well, now you're talking about a function. We won't worry about that for right now. Okay? All right.
X in it and it's not a constant.
Correct, exactly, since it has the x in it. So that'll be a little bit different. And we'll talk about that. And the derivative of e to the x, a little bit different, right? And I don't think we'll get to that, though, either. All right, so now, that's all well and good, but of course, we haven't done just constants, right? We've done all sorts of other things here. I'm actually going to go to another page because I don't think I'm having enough space if I try and fit it all in there. So now let's try and come up with something else here. All right, we're going to use the, whoops, sorry about that. I'll silence that. Use the definition of the derivative. Thank you. To find the derivative of the following, or the derivatives of the following. Okay, so here I'm going to show 3 different functions whose derivatives I want us to find. You do not need to do all 3 right now if you want to. I would like you to select one. Okay? I'd like you to select one and do the derivative using our limit definition, like the one we have up here. Okay? And we're going to find the generic derivative, which means we'll need to leave the x's in here, right? We're not going to plug a number in for the x's. We're going to leave the x's in and then simplify it. Okay? Down to something like this. Okay? So I'm going to give you 3 functions. You can pick any one of these 3 that you want to do. All right? First function, f of x equals x to the 3rd. Second function, g of x equals x squared. Third function, h of x equals the square root of x, which is the same as x to the 1/2. Okay, and in fact, I'd recommend you use the x to the 1/2 version, right, instead of square root of x. Okay, pick one of those 3, find the derivative using, again, that limit definition. Okay, and we're not plugging a number in for x. You need to leave just x, the generic kind of x in there when you're taking that derivative. Okay, so pick one and go for it. A and C are probably going to be the more tricky of the 3 there. B will probably be the more straightforward. Okay, so if you're, if you're not really unsure, if you're uncertain of your footing and stuff like that, B would probably be the way to go. Okay, but you're feeling pretty good. You want to, give yourself a little challenge. Try something out. A and C would be the way to go then. Okay, I will be doing all 3. So see what you can come up with here. Okay, I guess that's not going to work for me. It should be quantity. The x plus h both sub in for the x.
Oh, okay.
Yeah. Boiling out x plus h times x plus h times x plus h. Yes. So you know how to do that?
Yeah.
Okay.
I don't think so.
Piece at a time. Piece at a time. You do x plus h times x plus h, get that answer. Then take that answer times another x plus h.
But then you're, I
But what do
think
you do now?
what did 2x put, the 2hx times like another x?
It'd be 2x squared h.
2x.
Right? Yeah. So you should have x cubed plus 3x squared h plus 3xh squared plus h cubed. Right? Minus f of x. So minus x cubed. Right at the end there. The x cubes will cancel. Everything else has an h. Factor h out. 3xh squared plus 3h squared x, or xh squared kind of thing, and then h cubed.
Oh, there's no squares?
No, that's right. Yes. 3xh squared.
Oh, minus x.
Nope. Only for h. Sorry, yes. Plug in 0 for h. Sorry, yes. Plug in 0 for h. My apologies. Yes. Just 3x squared. You got it. Feels good, doesn't it?
Oh wait, okay, so then
Yes. Okay. Let's see what we came up with there. All right, so volunteer want to answer for letter A? Any volunteers for letter A? Natalie? You got 0. Okay, did you plug in? Don't plug a number in for x. What did you get if you don't plug in anything for x? Oh, you did plug. You didn't plug something in for x. It just all became 0 for you. Yes, you should plug 0 for h. You should have an h in the denominator. You can't have some h in the numerator there. Okay. Just 3x squared. Yes, 3x squared is right. Okay, letter A is 3x squared. Shh. All right, how about letter B? Someone got an answer here for us for letter B. Grant? 2x. 2x is right. How about letter C? Anyone do letter C?
I did that one. Can
You
you show
didn't do
that
that
one?
one. Did anyone do it? I got it. Yes, Simeon's got it. What'd you do? What'd you end up with?
The formula.
And that's all as far as you got?
Yeah.
Okay.
Can you show Steve?
E for effort, E for effort. All right, so, yeah. I student taught in Prince George's County, and they had A, B, C, D's, and E's. They didn't do F's, they did E's, and so we would always joke with the kids. E for effort, you know, so F is really what you get, but nothing. Anyway, all right, so there's the setup for letter C along with the first step. Okay, there's a setup for letter C along with the first step. So it's x plus h to the 1/2 minus then x squared all over h, right? So there's your f of x plus h minus your f of x all over h, okay? With square roots, and because we have a difference here, we want to rationalize. So you multiply then by the conjugate, okay? This creates a difference of squares kind of scenario here, okay? And you just imagine foiling this, right? So you have two terms, right? And two terms here. X plus h to the 1/2 times an x plus h to the 1/2. They're the same base. You add your exponents, it's x plus h to the 1. Okay? Then when you do your outer term, you're going to have a positive x to the 1/2, x plus h to the 1/2. But then your inner term will be a negative x to the 1/2, x plus h to the 1/2. So those middle terms will cancel. And then the last, negative x to the 1/2 times positive x to the 1/2, same base, add your exponents. So it becomes negative x to the 1.
You can do that all really fast.
Okay.
No, one
All right. Laura, question? Letter C, not for our class, no. But if you do move on to calculus, stuff like that, it'll be something that you'll need to be able to do.
Which means to the benchmark.
We did, if you believe it or not, we did problems like this back in the limits unit, actually. We did. We did do problems like this. So it could show up on the benchmark. It could show up on the benchmark, potentially. Could. It actually could, I'm thinking now. But we'll have some practice, you know, with it and stuff like that if you don't feel confident with it. I can talk it through a little bit here. Let me get my G's question. Yeah. So let me just talk it through one more time here. Talk it through one more time. Oh, my G go through first.
Thank you.
Right. So we're okay with this initial setup right here.
Yeah.
Okay. So and you're okay with the idea of multiplying by the conjugate, right? So we change the minus to a plus and multiply it. And we're really just multiplying by 1, of course, but you know. All right. So FOIL first. Right. Those are going to multiply together. Maybe I should do this for the video here. Okay, these two multiply together. They have the same base. So when you multiply two things with the same base, what do you do with their exponents?
What do you mean same base?
Same base as in these are exponentials, right? You have a base and then you have your power. So your bases are the same, so you add your exponents. So 1/2 plus 1/2 is 1. There's your x plus h to the 1 there, just x plus h. Okay? Then your outer and your inner terms are exact opposites of each other. Plus x to the 1/2, x plus h to the 1/2, minus x to the 1/2, x plus h to the 1/2. You see that? They're exact opposites. The outer is a positive version, and the inners are the negative version. Okay? And then these last two, right? You'll have a negative x to the 1/2 times a positive x to the 1/2. Okay? But again, same base. They both have an x for their base. So you add the exponents. 1/2 plus 1/2 is 1. So you just have minus x there in the numerator. Okay? Believe it or not. Okay? So, at this point, right, how can we simplify from here? What can we do in the numerator? What cancels? The x's. So cancel the x's out, and then you'll be left with an h over h times x plus h to the 1/2 plus x to the 1/2. Notice I did not distribute this h. I did not multiply the h. I did not distribute it here with this term. And the reason why is because what's going to happen now with these h's? They cancel. So I have 1 over x to the 1/2 plus x to the 1/2. I also plugged in 0 for the h there. 2. Okay, these are common. They're common like terms. And so we have 1 x to the 1/2, and we're adding another x to the 1/2. So if I have 1 x to the 1/2, and I add another x to the 1/2, how many x's to the 1/2 do we have? 2 x to the 1/2. Okay, 1 over 2 x to the 1/2. Or you could say that equally as 1/2 times x to the negative 1/2. Okay, so we good up to this point. Wait, hold on.
You put a 0 for the 8?
Yes. I did. I kind of did 2 steps there because I wanted to get her done. All right. So, why did I put us through this torture? Well, let's see here. Our original function for letter A was f of x equals x cubed, and its derivative became 3x squared. The original function for letter B was x squared, and its derivative became 2x. And the original function for h of x was, well, square root of x, but we wrote that as x to the 1/2, and it became 1/2 x to the negative 1/2. Okay? So, do you see a relationship here between the original function and its derivative? And if so, what is it? Ethan.
So what you do, you take the exponent
Take the exponent.
of the x.
Uh-huh.
You move out in front as a coefficient.
Yeah, multiply it in front to be the
and then you
coefficient.
subtract 1 from the
Subtract one from the power. That's exactly right. Yeah. So x to the third becomes 3x to the 2. X to the 2 becomes 2x to the, well, to the 1, right? Subtract 1 from the power there. X to the 1/2 becomes 1/2 x to the negative 1/2. Subtract 1 from the power there. Okay? Wow. So instead of having to do all this mess, okay, we can just use what is called the power rule. It's called the power rule. Okay? It's called the power rule. So, let me see here. So, power rule. If n, and that's a cursive n there, if n is a rational number, then the derivative with respect to x of x to the n is n times x to the n minus 1.
Okay, n is the power, right?
Uh-huh.
Okay.
And it's the exponent there. Okay? If n is a rational number, then the derivative with respect to x of x to the n is n times x to the n minus 1. Okay. This works for positive n values and negative n values. Okay, it works for positive and negative values of n there. Yep. Okay, so let's use that for some examples here. Find the derivatives of each. Okay. Let's go ahead and use that rule now to find the derivatives of each function rather than having to do it by hand. Okay. So let's do, I don't know, I'll start with some basic ones here. Let's do like g of x equals x to the 4th. Actually makes, yeah, okay, we can do that. Yeah. Okay. G of x equals x to the 4th. Okay. So then, g prime of x will be what? 4x to the 3rd. 4 times x to the 3rd. Exactly right. Okay. Just bring the power out front and then lower the power by 1 to get your new power.
You have to do prime. You have to write the prime.
G prime of x, right? Because we wanted to note that this is now the derivative of that original function g. Right? Let's try another one. Sometimes we may have to rewrite our function so that it's in the appropriate format. For example, the derivative of h of x. Okay. Okay. The derivative of h of x. Okay. We're trying to find if h of x is 1 over x, what's the derivative of that, right? So first of all, is 1 over x in the appropriate format here for the power rule? How do we need to rewrite 1 over x so that it is in this format? What is 1 over x equivalently in this format? It's the same as x to what power? The what? Negative first, or negative 1 power. That's right. Okay. Now that we have it in the right format, now that we have it in the correct format, we can take its derivative using the power rule. Okay. So part of the, care that you need to take here with calculus is that you need to match the function whose derivative you're trying to take with its rule, okay? It needs to really match, okay? So we have x to the n, here's x to the n. So what will h prime of x be then? Negative 1 x to the negative 2, yes, okay? Negative 1 x to the negative 2. Or if you like, we can now rewrite it back in the form it was, negative 1 over x squared. Okay. Either way is okay. Either way is acceptable there. Okay. Do a few more here. I'll use h of x again because I wasn't thinking when I wrote. H of x equals x. Okay. Or in other words, when you have just x, right, that's really x to the what power? To the 1. And so then h prime of x will be what? 1 x to the 0. But what's x to the 0? 1. So in other words, this implies just plain old 1. Plain old 1. So the derivative of x is 1. Now that shouldn't surprise us. We actually could have done this prior to this point, shortcutting, doing a shortcut too, because x, what's the graph of x? What is the graph of x? What will it look like? It's a line, right? And so what's the slope of this line going to be? Its slope is going to be 1, right? And so we get a slope of 1. It's always 1 because it's just a linear function. All right. What about, I'll do 2 more here, I think. What about the cube root of x? Is the cube root of x in an appropriate format for us to use the power rule here? Not quite. We can rewrite it, right? We can rewrite it, though. Cube root of x is the same as x to what power? 1/3. And so then its derivative will be 1/3 x to the negative 2/3. 1/3 take away 1 is negative 2/3. Okay, negative 2/3. Or if you like, we could rewrite it as, 1/3 cube root of x squared, like that. You want to rewrite it back in terms of like roots and things. Okay? All right. One more here, and then we'll move on to a few other things here. Lots more, but we won't go. We'll see how far we're going to go here. One more here I want to show us though. What's the derivative of pi squared? 0. But wait a minute, power rule. Pi to the 2. Bring the 2 out front. 2 pi to the 1. The answer is 0. Because what is pi squared? It's just a number. What's the derivative of just a number? 0. Okay, pi squared is constant. Its derivative will be 0. So do be careful, right? All of these apply because we are taking the derivative of a variable to a power. Pi is not a variable. Pi is a constant. It's always itself, right? It's always that value, pi. All right, I'm going to throw in a few other rules here real quick, but I think we should be... Okay, constant multiple rule. This one's not going to be very mind-blowing, but it's going to be important for us to just have, okay? The derivative with respect to x of c times f of x is equal to c times f prime of x. Okay? So in other words, our power rule up here, right? According to our power rule, we can only take the derivatives of things that do not have a coefficient or have a coefficient of 1, right? But now with the constant multiple rule, we can have other coefficients besides 1, right? We can have other coefficients besides 1. So in other words, like, if f of x equals 2x squared, f prime of x then will equal what? 2 times 2 x to the 1, or just 4x. Okay, so in other words, the power there, when you take its derivative, we bring that power out front and it multiplies with the coefficient there. 2 times 2 equals 4, and then x to the 1. Okay, so you can just do that. Okay, we also have the sum and difference rules as well. Okay, and we'll stop after this rule right here. Okay. The derivative with respect to x, I'm going to kind of put them both together simultaneously here. Okay, so if we have two functions that are being added together or two functions that are being subtracted, we want to find the derivative of that sum of the two functions or the derivative of the difference of those two functions. Okay, that is equal to the derivative of the individual functions added or subtracted together. Okay? In other words, you can break up. When you're taking a function's derivative, you can break up that function over addition and subtraction and just take the derivatives of the individual terms, you might call them. You might say. Okay? This is where you can say one of those fun logic statements, one of those statements that are true, but you have to think about it when you say it or when you hear it kind of thing. It's like the derivative of a sum is equal to the sum of the derivatives, right? Or the derivative of a difference is equal to the difference of the derivatives. Okay, the individual derivatives. Which one? Number 2? That is an h of x there. That's an h prime right there. Okay? So just as an example here, I want to do one easier one, one harder one. Did I leave you not enough space? Yes? No? Okay. So now we can take the derivatives of polynomials, right? Whole polynomials here. So like x cubed minus 4x plus 5. That's our function. F prime of x then will be, well, again, we see some subtraction and addition, right? So you can kind of organize this based off the terms. So we can take the derivative of x cubed, subtract the derivative of 4x, add the derivative of 5. So what's the derivative of x cubed? 3x squared. What's the derivative of 4x? Silence. It's not, the answer is not silence. So not 1, nope. So what x when it's written by itself is x to the 1. So bring the 1 out front. What's 1 times negative 4? Negative 4, right? And then it's x to the 0. What's x to the 0 though? It's just 1. So we just have minus 4 there. Just minus 4. Okay. What's the derivative of 5? 0. So it's plus 0. So we can just write 3x squared minus 4 then. There's our answer. Okay. One more I'm going to squeeze in here. I'll zoom in so I can do this. Okay. 3t cubed plus 5t squared minus the square root of t, all divided by t. We're going to find that derivative. Okay. Is this, well, do we have a rule to take the derivative of a quotient? No. Later we'll have one. After the after the benchmark, we'll learn how to do this. You can do it with a quotient rule, okay? But we don't really need to use that quotient rule here. We can actually do this one by ourselves here. How can we simplify this? How do you simplify something like this? You can factor out a t. Yep, that's one way to do it. You could also just break up the fraction. Let me see here. Break up the fraction over, so make it 3t cubed over t plus 5t squared over t minus root t over t. So in other words, just divide each one of these terms by t. So in other words, this will equal 3t squared plus 5t, and then, well, I'm going to have to do a little more step here. So what root t is t to the 1/2 divided by t, right? So 3t cubed divided by t gives us 3t squared. 5t squared divided by t gives us 5t. And then, well, root t, I change that to t to the 1/2. And what is t to the 1/2 divided by t going to yield? So t to the 1/2 divided by t, well, when we divide, right, what do we do with their exponents? Subtract, so it's 1/2 minus a 1, so negative 1/2, right? So minus t to the negative 1/2. All right. Remember, this is not calculus. This is algebra. Okay, we haven't done the calculus yet. We haven't taken the derivative. All we did was just rewrite it. Now we're going to do the calculus. Okay. So are we good up to this point? Any questions so far? Just on the simplification here? No questions on this? Okay, so what's the derivative of 3t squared? 6t to the 1, or just 6t. All right. What's the derivative of 5t? 5. What's the derivative of negative t to the negative 1/2? Okay, so this one got to take some, not negative 1/2. So bring the 1/2 out front there. It does become a positive 1/2. T to the, what do we do with our exponent? Subtract 1. So what's negative 1/2? Take away 1. Negative 1/2, yeah, or negative 3/2. I would suggest leaving it as an improper fraction there. And then there's our answer. Okay, but imagine trying to do that problem without this shortcut, using the limit definition. Yikes. Yikes. Especially with the square roots and stuff in there. Yep. Yep. Okay, so I actually do have an assignment for you here too to get some practice with this. Okay, it's going to be out of the book again, I believe.
Wait, do we not give any benchmark
Say again?
practice packets?
We're going to start that on tomorrow. I'm going to post it actually Google Classroom, and you guys are going to work on it there. I believe actually, or I guess I can make copies too if you'd like.
Do we do like in our notebooks?
Yeah, just do your notebook or something like that. Yep. Okay, your homework. Page 878, numbers 17, 29 to 36, 43A, just A, and then 59. Okay. Yep, still on the same picture. There's 878. Let's get a picture of it. Okay. If you would prefer to get started on the actual review for the benchmark, that's what we'll be doing tomorrow and the day after. Okay, I can post that to the Google Classroom as well. Okay. So if you prefer to work on the benchmark review, I'll post that as well. But I have this page 878 opened up right here too on the desk if you want to. But you got a good 20 minutes to get some practice in there.
After I fell, I didn't think it would hurt, and then I picked up a box and started